Hello and welcome to a very quick talk about LibreSoc to give you a bit of a high-level overview. In the abstract for the OpenTapeOut Dev conference, thank you very much for Matt for the invitation and opportunity to talk here. You'll find out a bit about why it is that we're doing this. So I thought it'd be good to go over a bit more about the how and the what. It's, One of the key things that we've done is following Simon Sinek's advice, those who know why they do what they do work smarter, is we've picked Python and picked a Python-based HDL in order to be more effective at what it is that we're doing. It is a Libre project. We are not on GitHub. This is to encourage and respect Libre ethical principles, and also to remain independent from a digital sovereignty perspective for commercial purposes. We maintain a standard mailman mailing lists and the usual golden, oldie but goldie Bugzilla bug tracker. Here you can see some of the NLNet proposals that have been accepted, and so we have at the moment, I think, €350,000 in funding, and another 100,000 on the way, which is to be approved, and we also have €200,000 from NGI Pointer. See now. For the 180 nanometer ASIC that we did, just one thing, this actually predates Open Road and Open Lane. We heard about it about a year after we were into the project, so we were committed to a TSMC IMEC thing and working with Sorbonne University. Which is why we haven't gone the Open Lane route. Now, here you can see a list of the banks and the pins. Now, this is actually generated by this is Markdown auto-generated output by a Python program. And a future version of it will have different mux columns ability, and will automatically generate a GPI pin mux. The Earl Grey project was inspired by this work, which dates back 3.5 years. Also auto-generated, believe it or not, is an SVG drawing which was sent to the foundry to tell them how to orientate the pins and put them in the package. This wasn't written by hand. There's part of the Pinmux program auto-generates its entire output. We considered it prudent to deploy, just like Microwatt team, to deploy software engineering practices. One of the key things is we're going to be doing a 3D GPU. That obviously means we need SIMD backends, and rather than have complete insanity, which would normally done, you'd have 10 times engineers, you'd have multiplexed massive amounts of code, or you'd do horribly complex ALUs. We decided to abstract this out so that the SIMD behavior was identical to that of scalar. So if x less than y in a scalar format, it was done exactly the same code in a SIMD context, and at the back end, it works out based on the partition masks what actually happens, whether it is 1 times 64, 2 times 32, 4 times 16, or 8 by 8 comparisons and EQs, independent EQs in each lane. Completely dynamic. Again, works smarter, not harder. We have one of the very, very early pieces of work funded by NLNet and we carried out was the creation of an equivalent version of Chisel 3 util. Queues, pipelines, ready valid signaling, the usual everything that you would expect, but it's actually missing from the original HDL library that we're using. So one of the most sophisticated ones actually was the pipeline API, which is divided down into combinatorial logics on one side. So you have an input spec function, an output spec function, and you have a processing function. That is completely decoupled from how it is actually handled. Whether you have a combinatorial pass-through, or a handshake or buffering, or even as we've found a thing, we're actually able to use the standard a standard HDL API to do FIFO. So you can have a pipeline API which has multiple numbers of inputs of buffering. But so and because just as Chisel 3 util library has API documentation, so does nmutil, generated by Sphinx. Now, the register file we have, again, using Python, we describe the registers on a per input base, per pipeline basis using that pipeline API back thing, input spec and output spec. You declare what registers and which register files and the size of the bits in it. And then here in a function, a Python function, which has absolutely nothing to do with HDL whatsoever, we take all of those specifications and turn them round into register files. So it's a dictionary of a dictionary of lists of these, and it's turned into the other way round, so that you can access them at the register file side, and connect up. Connect instruction, connect to the read ports, enumerating those specifications per register file name, and then enumerate by register file port, all of which is Python, and you end up with like a 5% ratio of actual Python code organizing data structures, of actual HDL code to real Python code organizing data structures, not hit yourself in the head repeatedly with a hammer trying to get VHDL or Verilog to be a Turing complete programming language, modern programming language, which it's never going to be. A second instance of that was in the Power Decoder, where rather than write it out by hand as in source code, what we did instead was did machine readable CSV files combined with machine readable forms of the instructions, and then you end up with some code that reads those files and then generates a switch, a hierarchical switch series of switch cases, which create your decoder. And again, we end up with something like a 3% ratio of actual HDL to number of lines of code. I think this is what, 600 lines of code, and there's about 10 lines of actual HDL. Oh, look, there's a switch and an HDL switch and an HDL case statement. it's a thing, but it means that we don't have to. I think what we can then do is use these exact same tables in simulators, in documentation, in formal correctness proofs, and so on. So anyway, moving on, we are at our next ASIC, our second ASIC. This is a top-level bug report for the pinouts, and here is what we're discussing online on the mailing list of what should go in it, and the number of pins, total number of pins, etc., and what package, links to all documentation, etc. So, hey, if you'd like to help, there is plenty of work to do, and there's plenty of funding to do it. Thank you very much.